So we've spent lots of time graphing sine and cosine and tangent and their, the reciprocal functions as well. And it just so happens that we're not graphing these, but we need to talk about the graph so that we understand why we are doing what we're doing. We're talking about the inverse trig functions. So inverse sine and sine and inverse cosine, right, and inverse tangent and all that. So we have lots of information here kind of prepared, but we want to take a look at the shape of our sine curve as an example to talk about what we're looking at when we're talking about the inverse of sine. And then we'll kind of apply those ideas to the inverse of cosine and the inverse of tangent. Right? So this first little bullet point is just reminding us that in the past we've been able to determine if a function has an inverse by passing the horizontal line test. All right, let's think about that with regards to the vertical line test. We would draw a vertical line to see if it behaves like a function, and if my vertical line, no matter where it's placed, only intercepts the graph in one point, that means there's one output for every input. It behaves like a function. But the question is, does it behave like an inverse? And when you give it the horizontal line test, it fails because my horizontal line will touch the graph in more than one place, an infinite number of places, right? Because the graph goes on forever in both directions. Another way to think about this is we would often take the shape of the graph and reflect it over a 45-degree line. So let's see what that would look like. Here's my tracing paper with the graph already prepped. There's the 45-degree line. We're going to flip it over that slanted line, and it looks something like this. Now the sine curve goes back and forth, but it goes indefinitely up and down. So you can see that fails the vertical line test. So in other words, we're saying if you have one input, you get lots of outputs. So that is not what we want. We don't want that. So we're going to limit the part of the graph that is duplicating itself. We're going to narrow the window down, if you will. So we're going to remove enough of the top and the bottom until we have a much narrower focus. And when you just take a look at this very narrow window, that is what we're looking at. And if we were to take that and just kind of take it over here to the box in the middle, what we're doing is we're taking that reflected sine graph and we're narrowing the window down until we have just that really small part of the original so that it can now pass the vertical line test. So in other words, what we're doing is we're taking the sine curve and we're narrowing it down like this. We're only using a small part of it, and then we're reflecting that part across the 45-degree line. That way, we can now use the inverse sine. What is happening here then is we're limiting what part of the unit circle we're pulling our data from. So if we take a look at one sine curve and we're thinking, where did these critical points come from? Well, this first part here came from quadrant 1 of the unit circle. This next part of the curve comes from quadrant 2 of the unit circle. The next part comes from quadrant 3, and the next part comes from quadrant 4. And what we're doing is we're throwing out all of those pieces that would cause it to fail that horizontal line test. If we go in the other direction, we can include this quadrant, but not any more than that, because now it would fail the horizontal line test. So we're just keeping it that very narrow window. So in other words, we're saying quadrant 1 and 4 from the unit circle are the values we're using to plot this curve. And so on our inverse sine function, we're not graphing this, but this is what it looks like when you've chopped off the top and chopped off the bottom. What that means is we are only using quadrants 1 and 4 from the unit circle. Quadrants 2 and 3 don't exist anymore. We've thrown them out because we removed the part of the graph from which they came. What that means for us practically is that we cannot rotate through quadrants that don't exist. I can only rotate counterclockwise into quadrant 1 or clockwise down into quadrant 4, which means we're going up to positive pi over 2 or we're going down to negative pi over 2. In other words, it's impossible to have an angle of positive 3/2 pi because you can't rotate through quadrants that don't exist. So we're applying the same technique with our cosine graph. We're throwing out a big part of it, and we're only keeping this much. Quadrants 1 and 2 for the inverse cosine. Quadrants 3 and 4 don't exist anymore. We've thrown them out. You can't rotate through those quadrants because they're not there anymore. So that first one that we looked at, it's in very tiny print, but we're talking about the inverse sine function. There it is. The second part here, we're talking about the inverse cosine function. And the third part here, we're talking about the inverse tangent function. All right. So with the inverse tangent, we're back to quadrants 1 and 4 only. So again, you rotate up into quadrant 1 or you rotate down into quadrant 4. So that means the kinds of answers that we give are limited to just these quadrants. Now, notice nothing comes from quadrant 3. So before we start working with those kinds of problems, let's do a real quick review on how we could write this in inverse form. All right, so here you have an input, right? There's your angle of rotation on the unit circle, and there's your output. So what we're saying is, on the unit circle, cosine is paired up with the x-coordinate. So when I rotate to pi over 2, I'm at the top of my unit circle, and the x-coordinate that I find at pi over 2 is 0. Now what we do when we write the inverse is we exchange the input with the output. So now we're plugging in 0, meaning we're starting off with the inverse cosine of 0, meaning I know my x-coordinate on the unit circle is 0, so the question is, where am I? We're always solving for an angle of rotation. The angle is the answer to an inverted, and I should say an inverse trig function. All right, so cosine pi over 6 equals root 3 over 2. So again, an x-coordinate here at that angle of rotation gives me this x-coordinate. So now we can either write it as cosine inverse or we can write it as arc cosine of that x-coordinate, and that gives us an angle of rotation. Where are we? We are at pi over 6. With arc sine, now we're talking about the y-coordinate on the unit circle. The y-coordinate is root 3 over 2 when I'm at pi over 3, so let's exchange these now. Sine of my angle of rotation is the y-coordinate of root 3 over 2. The last one here, the arctangent, or the tangent inverse of 1, is found at pi over 4. So that means tangent at pi over 4 is equal to 1. Right? So we just exchange the inputs with the outputs when we're converting from a trig function to its inverse or from an inverse back to the original trig function. So the next few problems we're going to be focusing on the quadrants and what values we can get when we're evaluating. So let's go over to the next page, and I'm really focusing on just the problems that I've circled because those are the ones that come from the unit circle. These other problems that I'm skipping over, those are just calculator problems, and so you see a little calculator display information piece up there, and I'm just skipping over those. Let's focus on the unit circle. All right, so example 1, arc sine. Remember, the answer to an inverse sine function must be an angle of rotation. So the question is, where am I? How many radians have I rotated to get to this place? So sine is paired up with the y-coordinate. The y-coordinate is the root 3 over 2. So the question is, where am I? So that my y-coordinate is root 3 over 2. Remember that with arc sine, you're only allowed to use quadrants 1 and 4 on the unit circle. So we can rotate this way to quadrant 1 or clockwise to quadrant 4. This is a positive y-coordinate, so that means we're rotating here. That's our angle of rotation. That's pi over 3. All right, here's number 2. Sine inverse of 0. Again, this 0 is the y-coordinate. So the question is, where are we? What's the angle of rotation? So we're still using inverse sine, so we can look at this sketch again. Right here, that's where we're at. So the answer is 0. But notice this 0 is different than the original. The original 0, that was your y-coordinates on the unit circle. But this 0 is the angle of rotation. So you're thinking, how many radians is it? It's 0 radians. So you don't have to write the 0 pi, but that's so you can see that these two zeros are meaning different ideas. Arc cosine of negative root 3 over 2. All right, with arc cosine, we are only allowed to use quadrants 1 and 2. So where would we find an x-coordinate that is negative? That has to be in quadrant 2. So the question is, where am I? What is that angle of rotation? That equals 5/6 pi. Here's number 6. Arc cosine is negative 1. All right, so again, we're using the same sketch as before. We can only use quadrants 1 and 2. So where are we when my x-coordinate is a negative 1? That has to be right here. What is that angle? Pi. So that equals pi. Number 7, inverse tangent. So inverse tangent, just like inverse sine, can only use quadrants 1 and 4. So the question is, where are we when my tangent ratio is 0? So remember, tangent is sine over cosine. Tangent is the y-coordinate over the x-coordinate. So we're asking ourselves, what y-coordinate and what x-coordinate do I have such that they simplify to 0? And then where are we on the unit circle? So we want to take a look at a point like this one, because here we have 1, 0. And so if we were to set up the ratio of the coordinates in this way, that means the tangent inverse at 0 equals 0. Again, this 0 is the angle of rotation, so think of it like 0 pi. Here's the last one in the series, number 9. Arc cosine of pi. Now this is kind of weird. This is kind of a trick question, if you will. Remember that that's just going to be a decimal value of about 3.14. So the question is, what angle of rotation am I at on the unit circle when my x-coordinate is 3.14? So if we're only allowed to use quadrants 1 and 2, what kind of x-coordinates do I have? Well, we have 1, 0 to negative 1, 0. In other words, I don't have an x-coordinate of 3 anywhere, because no x-coordinate can be bigger than 1 or smaller than 1. So this is outside the domain. So this is actually undefined. There is no angle of rotation. And that's why we have to be very careful of what we use for our inputs and our outputs. Normally pi is just an angle of rotation. It should have been here, but no, it was, I don't know if accident is the right word, it was placed here, which is wrong form, and you can see we can't even evaluate that because there is no possible way to have an x-coordinate of 3.14. All right, here's the last one, number 10. So this is a little bit different. We're still on the unit circle, but notice it's set up as if you are taking the arc cosine of the cosine of an angle of rotation. So it's a sequence of events here. You want to think of this like doing your order of operations, where you do what's in the parentheses first, and then we'll take the arc cosine of that answer. The danger here is saying, wait, doesn't just the cosine and the arc cosine, don't they just cancel themselves out? Isn't my answer 7/2 pi? No, it isn't, and we have to think about why that is. So we start with what's on the inside, and if it helps, here's our unit circle. Now remember, we're using all 4 quadrants because this is the normal cosine. You could rotate all the way around in both directions. So where is 7/2 pi? So here's 1/2 pi at the top, 2/2, 3/2 pi, 4/2 pi, 5/2 pi at the top, 6/2 pi. Here we are at the bottom with 7/2 pi. So there's the angle. So in other words, we have rotated around to this point. So what coordinates do we have right there? That is located at 0, -1. So we're asking, what is the cosine at that angle of rotation? Cosine is paired up with x. There it is. So this is the result. We want a 0 right there. So that means we are taking the arc cosine of 0. So now we're reversing the process. Arc cosine is paired up with the x-coordinates. We're saying this is the x-coordinate. Of course it is. We just found it. This is the x-coordinate. So the question is, where am I? What's my angle of rotation? And you might say, isn't that the angle of rotation? Weren't we just there? No, because remember that with arc cosine, you're only allowed to use quadrants 1 and 2. We threw out 3 and 4, which means these numbers that we got, they don't exist anymore. We need different values instead. So on quadrants 1 and 2, where's my x-coordinate, the cosine? 0. And here we are at the top, 0, comma, positive 1. What is that angle of rotation? Positive pi over 2. So notice the answer that we have is not the same as the angle that we started with. So in other words, don't just assume that cosine and the inverse just cancel themselves out when you're on the unit circle, because we are restricting which domains. We're restricting the quadrant, and that impacts the domain that we're allowed to use.